when certain objects are packed in containers, they do not occupy the entire volume of the container. This occurs due to the shape of objects, and under such situations, a fraction of the container volume is always empty and filled with air. Consider a container in the form of a cubical box of side length 8 r, which is fully packed with identical solid spheres of radius r in a regular manner, as shown in figure 1. This is called regular packing. Part A. Find the number of spheres packed in the container. Now, length, breadth and height of container 8 r, which is a cube, and radius of a solid sphere r. When considering the lengthwise row, length is 8 r, length of the container 8 r, diameter of sphere is 2 r. Then we can pack 4 spheres in lengthwise. Same thing, we can pack 4 spheres in breadthwise and 4 spheres in heightwise. Then we can get total number of spheres we can pack in the container 4 into 4 into 4, 64. Then part B, obtain an expression for the total material volume of all spheres packed in the container in terms of phi and r. We can get volume of a sphere 4/3 phi r cube. We have to multiply by 64 to get total volume. We can simplify it. 4 into 4, 16, 1 remaining, 4 into 6, 24 plus 1, 25, 256 pi r cube divided by 3. In part C, when the container is completely filled with spheres, the ratio total material volume of spheres in the container divided by volume of the fully packed container is called the packing fraction Fp of the spheres, and the volume of the fully packed container is called packed volume. Find the packing fraction Fp for the above regular packing. Packing fraction means total volume of spheres 256 pi r cube divided by 3. We have to divide by the volume of the fully packed container. It means volume of container, length into breadth into height, 8 r into 8 r into 8 r. Now I will simplify it. 256 pi r cube divided by 3 multiplied by reciprocal, 8 r into 8 r into 8 r. We can cancel out r cube and we can cancel out by 8. 8 divided by 8, 1, 3, 2. 8 divided by 8, 1, 4. 4 divided by 4, 1, 2. Then 5 divided by 3 into 2, 6. 5 divided by 6 is the packing fraction. Then part D, if M is the total mass of the sphere in the container, derive an expression for the ratio total mass of the sphere divided by volume of the fully packed container in terms of M and R. The ratio is called bulk density dB. We can write bulk density. This one is part C. Now part B. Bulk density means total mass of sphere divided by volume of the fully packed container. It means volume of container. Volume of container is this value, 8R into 8R into 8. 8 into 8, 64. 64 into 8, 512 R cube. You have to substitute 8R into 8R into 8R. Then part E. Write down an expression for the density dm of the material of spheres in terms of m, r and phi. Density of material. We know that volume of sphere is 1. Mass of sphere, simple length. Then we can write density equals to density dm के लदी लदी हो. Density dm equals mass divided by volume. Mass divided by total volume is total volume of sphere. This one 256 pi r cube divided by 3. We can write it 3m divided by 256 pi r cube. In part F, a student has decided to find the parameters Fp, dB and dm. Fp means packing fraction, dB means bulk density, dm means density of material. Are varied for dm for use for green gas using an experimental method. In this case, green gas is packed in random manner. It is called random packing. See figure 2. The definition mentioned in part C, D and E for Fp, dB and dm are varied for random packing of items of any shape too. First he inserted dry green gas into a measuring cylinder and obtained a packing volume 50 cubic centimeters of green gas as shown in the figure. Then he measured the mass of packed volume 50 cubic centimeters sample of green gas and it was found to be 3.8 into 10 to the power minus 2 kilograms. Subsequently, he introduced the green gas sample into a measuring cylinder containing 50 cubic centimeters of water and found that water level raised to 82 cubic centimeter mark. See figure 3. Part 1. What is the material volume of green gas? We can get material volume by using the third figure. Before introducing green gas, initial water volume is 50 cubic centimeters and after producing green gas, final volume is 82 cubic centimeters. It means displaced water volume is equal to the material volume. Then we can get F part 1 increased water volume is 32 cubic centimeters, or we can write in SI unit. When converting cubic centimeters to meters, we have to multiply by 10 to the power minus 6 because of there is a third power. Value of 10 to the power minus 2, we have to put 10 to the power minus 6 when removing centi prefix. In part 2, calculate the packing fraction SP of green gas. Right, we can get packing fraction. Packing fraction is defined as the total material volume divided by volume of fully packed container. Total material volume 32 cubic centimeters we have found in part 1. Packed volume is, according to figure 2, 50 cubic centimeters. Both are in cubic centimeters, therefore we can write it as the answer. We can get values without unit conversion. Then we can simplify it, divide by, I will multiply both terms by 2, then 64 over 100. It means 0.64. In part 3, calculate the bulk density of the green gas in kilogram per cubic meter. Now we have to use SI unit. Bulk density is mass total mass of material divided by volume of the fully packed container. Therefore, we can consider mass of the green gas volume is given as 3.8 into 10 to the power minus 2 kilograms. Then bulk density 3.8 into 10 to the power minus 2 kilograms. It is the mass of green gas. Then we have to divide by volume of fully packed container means 50 cubic centimeters. We have to convert to cubic meters. 10 to the power means 6 minus 6 cubic meters. We can simplify it. Again, I will multiply both terms by 2. 8 into 2, 16, 1 remaining. 3 into 2, 6 plus 1, 7. 7.6 divided by 100 into 10 to the power minus 6. In numerator, there is a 10 to the power minus 12. Then we can cancel out minus 2 and minus 6. 10 to the power minus 4. Again minus 4 and 100. 10 to the power minus 2. When dividing 10 to the power minus 2, we can get it to the numerator as a multiplication. 10 to the power 2. 7.6 into 10 to the power 2. Unit is kilograms per cubic meter. We have used SI unit. In part 4, calculate density of material of green gas in kilogram per cubic meter. Now we have to use mass of green gas and actual volume of green gas. Density of material, mass, same value, 3.8 into 10 to the power minus 2, divide by volume is found in part F1, 3.8, 2 into 10 to the power, we have found 32 cubic centimeters. 32 into 10 to the power minus 6. Then we can simplify it. 10 to the power minus 4. I will bring it to the numerator. Then 38,000 divided by 32. We can cancel out by 4. 8 divided by 4. 9, 36. 20 divided by 4. 5, 0, 0. 9 divided by 8. 1. 1 remaining. 15 divided by 8, 1, 7 remaining. 70 divided by 8, 8, 64, 6 remaining. 60 divided by 8, 7, 56, 4 remaining. Point 40 divided by 85 kilogram per cubic meter. Then part G, a polythene bag is to be designed to pack 1 kilogram of green gas. Calculate the minimum volume of the bag needed. We know that when packing green gas in a polythene, there are spaces, air-filled spaces in polythene. Therefore, we have to consider bulk density. Bulk density is total mass divided by volume of the bag. Now, total mass is 1 kilogram divided by volume of bag. We have to find the value of volume of bag. We can substitute bulk density, this value, 7.6 into 10 to the power minus 10 to the power 2, 1 over volume. Now we can get volume 1 over 7.6 into 10 to the power 2, approximately 1.3 into 10 to the power minus 3 cubic meters.